So welcome back, everybody, to the 2026 Langtangen seminar. We're very happy to have with us today Yunan Yang, who is a tenure-track assistant professor, or Goenka family assistant professor in the Department of Mathematics at Cornell University. Yunan earned her PhD in 2018 at UT Austin, where she worked with Björn Engqvist. Prior to joining Cornell, Yunan had several prestigious positions around the world. So she was an advanced fellow at the Institute for Theoretical Studies at the ETH in Zurich. She was a Simons Berkeley Research Fellow and a Courant instructor at NYU's Courant Institute of Mathematical Sciences. She has many research interests in applied mathematics. Some of them cover some of the talks we've had already this year and last year, and some of them we haven't seen yet. In particular, inverse problems, optimal transport, numerical analysis, non-convex optimization, and machine learning. And her talk today is when optimal transportation meets PDE-based inverse problems. So Yunan, the floor is yours.
Oh, thank you very much, Thomas and Marie, for organizing this seminar. And I'm very flattered to be invited and to give this seminar and talk about two of my favorite research topics. One is optimal transport, and another is inverse problem. So what I've been doing starting my PhD now is more than a decade. What I've been doing a lot in my research is to combine these two together and use optimal transport or measure transport in general as a tool to solve some challenging inverse problems. Okay, so first of all, I want to just briefly revisit what is the inverse problem. So inverse problem, in my view, consists of two things. One is data. Right? Inverse problem is all about how can I infer some information from data. So data is an essential part, and most of the time the data are in pairs. So you have a probe or echo X, and you probe this model you don't know much about, and this is all the inverse problem's whole goal is to understand better about this model. You probe the model, and then you have Y. So data come in pairs as X and Y pairs. And we want to use that as ingredient number one to understand better about the model. So for an inverse problem, the model is predefined. So you are given the model. So for example, you are giving the heat equation and you are asked the question, okay, what's the source? Or you are given a wave equation, you are asked the question, what is the wave speed, the C in that PD? So with these two ingredients, one is the model, another is the data, we are interested in a particular parameter inside the model. Okay, so with this as a very general inverse problem, you can imagine the model is not necessarily tied to PDEs, ODEs. It can also be things like neural network or graph model or something like image convolution, etc. So that's the general picture of inverse problem that I would like to position this talk on. Okay, so to give us a few concrete examples and which will also show up later in my talk. So what you have on the right-hand side on the top is the scalar wave equation, or also known as acoustic wave equation. So this is where I first apply optimal transport to as an inverse problem. So this equation we know is a linear equation we learned in PDE 101 courses. The linearity, however, is respect to the source term or the boundary condition. Unfortunately, in a lot of application regarding this wave equation, we are interested in this variable coefficient m of x. So m of x is 1 over c x squared. C has a physical meaning. C means the wave velocity. So for example, water is 1.5 kilometer per second, and then there's like other units as other salt is 5 kilometer per second. So different material have different speed. So this is exactly how geophysicists or medical imaging professionals use this wave speed to identify the material and then have more post-processing processes. Okay, so for example, some events happen, maybe we have an earthquake, and on the top of the Earth's surface, we record the wave field, and the wave field is in both space and time. So the vertical direction is time. The horizontal direction represent different receivers. So when I stack them together, they look like time of Vigo, and that's very valuable information. And in real this situation, this is the wave speed, this is the wave data we record at the boundary, upper boundary, that we want to use to infer what is going on underneath the surface, like inside the Earth's interior. And that's the m of x we are interested. This is a problem that established since 1980s and a lot of work, but also a lot of challenges I will talk about later. And the next inverse problem is actually connecting to the talk last week given by Mike Holbrook from Cambridge. So this is under the big umbrella of learning the dynamics. So when we say learning the dynamics, usually it's because you observe, let's say, trajectory. So when I say trajectory, you can imagine it's like samples of the ordinary differential equation solutions. So you don't get to see what is the right-hand side of the ODE or what is the right-hand side of the SDE. If you know what's the right-hand side, that means you know the model. You can simulate it, you know everything about. So inverse problem is about you don't know them. So you don't know the right terms. What you have as a weapon for you at your hand is you know the data simulation along this trajectory. So for example, you may observe this attractor on the left-hand side. And the goal is with this attractor I observe on the left-hand side, can I infer the driven mechanism of this dynamics? So for example, can be the velocity on the right-hand side or velocity plus diffusion. So this inverse problem, well, I consider the inverse problem actually it has a big community. It involves people in biological science, involve people in aerospace engineering, and also social science. Because such whenever ODE, SDE, and the corresponding focal Planck equation become used for modeling, then that's where such inverse problem will pop up. There's a lot of work solving such inverse problem. For example, Cindy using polynomial or some other dictionary by estimating the velocity that fit the coefficients, or some neural network weights such as neural ODE, or some other like non-parametric methods. Kuhlmann and the Frobenius transfer operators, they all sit in this big umbrella of solving the inverse problem of learning these V's and the sigmas, for example. Okay, so those are two examples of a particular inverse problem and how do we solve them in practice. Unfortunately, it's very hard to solve inverse problem like equation. So inverse problem, in overall, I want to solve g equal to f of m. That's an equation, where it's an infinite dimensional root finding problem. But it's difficult because I don't know f explicitly and it's infinite dimensional. So in practice, most of the time, we translate them into an optimization problem. So we take a step back, saying rather than trying to answer the question g equal to f of m, try to find m, we try to minimize the difference between g and f of m. So now we have a loss function or objective function that penalizes the difference between the data g and the simulated prediction f of m. And then this becomes something as a function or functional of m. And our goal becomes, okay, I'm just trying to find m star, whoever can minimize this. So this is a translation from an equation to a variational problem, very similar to like in linear algebra, we translate a linear system to a least square problem. So there's a one-to-one correspondence. So once we do this translation, a lot of the difficulty can be kind of not diminished but translated into corresponding element in optimization. Since optimization is very developed, so there's a lot of powerful tools for us to maybe get an answer. It may not be the correct answer, but at least from a practical perspective, I can try and play around, and maybe I would get a very good M star. So once we are in this framework, some terms that you may heard about is like a PDE-constrained optimization. So that is a common byproduct you will obtain after turning this into a variational problem. And my talk focus on two things. One is you need to be careful about what you choose to measure the misfit between your data and your model prediction. And another is we need to be careful of which geometry or which metric space you are searching for your parameter. So those are the two places that are often overlooked in practice. But what I want to have a takeaway message for you by the end of the talk is that just without changing anything else, just by carefully designing these two metric spaces, you can actually change the performance of your inversion. Okay, so this is a very optimal transport come into the play. And optimal transport is what I would consider a very unusual metric space to consider in comparison to Sobolev spaces that we have been learning a long time ago. Okay, It's just a brief history of the evolution roadmap of optimal transport as a field. It started in 1781 by French engineer Monge. Is also the Monge in Monge empire equation. So Monge has, it was, I think, just after the French Revolution, and Monge has this problem of doing constructions, and he has a big pile of sand, and he want to move this big pile of sand to somewhere far away, that let's say another location like a big hole. And since they are so large, we cannot think they are point mass. If you cannot think this two pile of sand or as a point mass, then how you move them really matters. So one way to move them is left to left, middle to middle, right to right in a monotone way. Another way to move is like right to left, middle to middle, left to right. That's another way. And so these two ways, what behind them are two different function S. So Monge asked the question, which function S I should use to dictate how I move mass from X to Y? So it's a very simple question. He wants to choose a way that is the cheapest in some economical setting. It's one sentence to explain the problem, but take hundreds of years to solve for two reasons. One is he's searching a function, and back in 1781, there are not so much mature mathematical tools to optimize over function spaces. And the second, the way that he originally formulated the problem is quite nonlinear with respect to the function S. It's nonlinear, so it's nonlinear infinite dimensional optimization, even very difficult nowadays. So what the Kantorovich did 200 years later was relax the problem a little bit. Rather than saying a mass at the location X has to go to everything at the location Y, he allowed mass to be splitted. So let's say you take mass from location X, but you give part of them to Y1, part of them to Y2. So like if you split things from X to Y1 and Y2, this is no longer a function. Yeah, function does not allow you to have two outputs. Although he breaks the function requirement, he can make the problem linear with respect to what you want to find. And at that moment, linear programming can kick in. So practically, they immediately see the benefit of considering optimal transport. And there's a lot of economical applications due to this new formulation. Okay. And it's just a side remark, Kantorovich also won the Nobel Prize in economics in 1975, not only due to his contribution in optimal transport, but also due to his contribution in many things in operation research. And later on, there's a lot of analysts. You can see some Fields medalists, some Nobel Prize winner contribute to this theory of optimal transport. And by the end of 20th century, theoretical aspect of optimal transport on the classical sense are very complete. And that's why starting 21st century, we see very colorful application in data simulation, hyperbolic model reduction, image processing, inverse problem, machine learning, sampling, etc. And what I focus on, my research sits towards how optimal transport can help us with inverse problems. And this is also the evolution of this field starting the end of 20th century towards like a couple years ago. And this number of publications involving keywords in optimal transport, such as optimal transport, Wasserstein distance, Monge, Kantorovich, Earth mover, etc. So this is really rapidly evolving with a lot of excellent researchers are contributing to the field. Okay, so let's zoom in into like what is in essence behind the optimal transport. So it really sits towards Monge's original problem. You have a two pile of sand. Now it's simplified to three bars. I have two histograms. They are not the same. And I want to measure how different they are towards each other. So what we do and what optimal transport does is rather than just subtracting and doing the pointwise component difference, we first see how can I make them the same. So moving the extra mass from the first bar to the second bar, they become the same. So this is where the transport map is doing. I move around and make them the same. And once I make them the same, then optimal transport is capture how much effort in the process I spend to make them the same. And the effort is measured in this very particular way. It's the amount you moved. You carry this amount of mass, and it's multiplied by the distance squared. So what I lay in front of you is really kinetic energy. So you can interpret that this is m and this is like v squared. Later on, if I talk more, actually it's like a constant geodesic. So the distance moved is directly corresponding to the velocity. So this is really mv squared. So at every point, we care about both the vertical differences in m and the horizontal difference in distance. And that's, in my mind, what make optimal transport very unique. It's not just one-dimensional, only y direction. It's also not just one-dimensional, only in x direction. It's at every point, the two directions are coupled together in terms of energy, kinetic energy. Okay, so the mathematical definition is the one-to-one correspondence to the cartoon. I have two probability distribution. P of omega means the probability distribution over the space omega. And I want to find a map T. So this T can rearrange F into G. And once T, so M is, yeah, the set of all maps. So sometimes you have more than one. Okay, so if there's so many maps that can do the rearrangement, I calculate the horizontal difference, the distance, and then that is multiplied by the mass. F of x is like the density at the point x. So these two together is the kinetic part, kinetic energy part per point. And then we integrate over the entire domain that give you the total energy you spend corresponding to this particular map T. And the optimal come from that among all possible maps, we select the ones that give us the minimum cost. So this is Wasserstein distance. So this quantity is the Wasserstein distance, which is the square a piece root of the transport cost. So P is like LP norm. P can be anything between 1 and infinity, and it will still make it a distance. But in my talk and a lot of my research, I focus on P equal to 2 due to the nice differentiability and its connection to autocalculus and pseudo-Riemannian manifolds that we will see later. Okay, so from now on, I'm going to tell you why I would like to use this weird-looking, infamous something distance to solve PDE-based inverse problem and what you can gain by doing so. Okay, so first thing I want to tell you is you can improve your optimization landscape. Let's look at a very simple example. In wave application, which I started with, we are comparing one wave field and another wave field. And the wave, as we know, they travel like a sinusoidal, like a sine function or cosine function or method of characteristic. It travel along the characteristics. So now let's see, I have this blue wavelet and I have the red wavelet. The red wavelet is purely a translation of the blue wavelet. And I want to measure the difference between these two. So this is a very simple question. I have mismatches wavelets and they can come from an incorrect estimation of the wave speed. Right. So if I estimate wave speed wrong, then one may arrive much later than it should be. So this happens very often in the wave inversion problem. And if I just compare them pointwisely by your favorite least square method, then you can see I have a terrible, terrible optimization landscape, which is very not favorable for a gradient-based method. You have so many local minima, so many local maximum. Yeah, this is a nightmare to optimize with. You can only be lucky to convert to the global minimum if you start with this very thin strip. And the probability of starting from this thin strip is very low if you don't know a lot about the prior knowledge. Okay, in comparison, if I just use the Wasserstein distance I introduced you a previous slides ago, then you have a global convex optimization. And this is a drastic contrast to the left. And that's it telling us when you are dealing with things that with transport matrix, just a simple change of objective function, you can go from a terrible optimization problem to a very nice optimization problem. Yeah. So when people who are, let's say, doing complete neural network training or doing PDE-constrained optimization, a lot of difficulty we face is non-convexity. Like, so optimal transport is what I consider a very good tool to mitigate some of the non-convexity issue existing methods struggle with. Okay, so this is an inversion result based on the wave problem I showed at the very beginning of the talk. So on the left column is the L2 inversion, and on the right column is the Wasserstein inversion. So in both cases, we don't know the ground truth. So Yeah, okay. So in both cases, we start with the same initial condition. And after 300 BFGS optimization algorithms, the L2 inversion convert to something we like express a local minima everywhere. But even if you don't know the ground truth of the Mamousi model, which I show here, just look at the data residual. It still shows that the L2 inversion is not doing a good job because our ultimate goal in inverse problem is to feed the data. I have a G and I want to find an M such as f of M fit G. And the residual is the difference between f of M and G. And you can see there's so much stuff going on. So it's not fitted at all. So this is a indicator that the L2 inversion stuck at the local minima. And in contrast, the W2 inversion recovers the correct Mamousi benchmark. But also, if we don't know what is the correct solution, just by looking at the residual, a lot of the waves are gone. So if you are very like careful, there's a little bit left. But the things that are left are high frequency components that I have explanation why they exist. But the majority of low frequency components responsible to the uh, the uh, the recovery of the Mamousi model, they are gone. So it's also indicated that the Wasserstein distance overcome the local minima issue, the L2 struggles. Okay, so another high level why Wasserstein distance would be a very good example is most of the time when we stuck, like in PD control optimization or in machine learning training, when we stuck is when gradient is zero. So in this type of data-driven mechanism, your gradient has two components. One is dJdF, the derivative with respect to the data. Another is dFdM, is the Jacobian from your model propagating to the parameter. So this is the Chen rule. The reason we have a Chen rule is because you try to find the parameter by fitting the data. So data is the intermediate middleman. So that's why you have a Chen rule over here. So when gradient is zero, let's see examine when that happens. So dJdF, even if J, let's say, is a least square method, is the L2 norm. L2 norm is convex with respect to F. So F minus G squared, the derivative F minus G is only zero if you match the data. So most of the time when you have like a local minima trapping, it's not because the right term is zero. In other words, the right term is zero only if you already feed the data 100%. Okay, now let's look at the blue term. The blue term is the Jacobian. If your model is good, let's say if your model does not have degenerate information, does not have redundancy, then your model should be full rank as a Jacobian. So most of the time, if I choose a good model, the blue term should be full rank. So that also shouldn't be the model. That shouldn't be the problem that I see zero gradient. Okay, if that's the case, then there's only one possibility that I see zero gradient. That is a projection of dJdF over the column space of the FDM. The projection is zero. Okay, so that is the mismatch between the choice of your objective function and the choice of your model. Thinking about the wave problem again, wave like to travel in horizontal direction. That's when parameter change it like to travel like a crab going horizontal direction. But L2 norm like to move in vertical direction. And then L2, like in the derivative, tell you, okay, you need to go this way. And then you project that this vertical direction over the Jacobian of the wave model. The wave model tells you, wait a second, my model is designed to move horizontally. There's nothing I can do to move things vertically. Okay, since there's nothing I can do, so I'm not going to do anything. So that's actually why most of the time we have zero gradient. It's the incompatibility between your model and your choice of objective function. And a good choice that especially aligned with the model can overcome such an issue. And that's why in follow-up work, we can see motivated by this wave problem, we can see in other scenario of inverse problem, you can also benefit from using Wasserstein distance as long as your model exhibit some transport global transformation phenomenon. For example, reconstruction from projections or reconstruction from localized sources or deconvolution from diffuse environment. So then this allows us to go beyond hyperbolicity. So the story is that you do not have to use optimal transport for wave problem, as long as your inverse problem, the parameter to data map has sort of a transport or global transformation nature, then that would be a situation optimal transport will be very helpful to make things more convex. Okay, so next I want to move to my second property, which is robustness to noise. So this part is related to some very nice analysis related to the property between Wasserstein distance and Sobolev H-1 norm. In asymptotic setting, when you have two measures and one is a perturbation of the other, one can do this asymptotic setting from Otto-Villani 2000 work. The Wasserstein distance is asymptotically a weighted H-1 semi-norm. And 20 years later, by Remy Prairie, a French mathematician, he also realized that in a non-asymptotic setting, as long as f and g have densities and the density are upper and lower bounded by some constant, then I have a very neat equivalence between the Wasserstein distance and the H-1 semi-norm, unweighted. And if you have like singular measure, then based on what we know of Sobolev embedding, you actually can embed the property measure in a much weaker negative Sobolev spaces. But all three results are implying that the Wasserstein distance, if I want to place it in this roadmap of Sobolev spaces, WKP spaces, then it should be sitting very close to H-1. Okay, so now let's look at what's the property of H-negative space, H-negative norms and H-negative spaces. I am going for the Fourier transform definition. So something's HS norm is that you first take the Fourier transform of the input, then you get this component as a function of a Kc, and then you weigh the Kc component correspondingly. So I consider all the L2-based Sobolev spaces as a weighted L2 space, and the weight come from the spectral component. So when S is negative, that means you weigh the higher frequency components very little, and you weigh the lower frequency component very much. So in other words, when you have a negative S, you are having a smoothing operator. So when S is negative, this is a physical domain representation of the minimizer. The physical domain representation of minimizer involves this integral operator when S is negative. So this integral operator applied to your noisy data is doing a smoothing and a cancellation, especially for high frequency data, for high frequency noise. So when you use a negative Sobolev norm, or correspondingly also when you use Wasserstein distance, you are benefiting from choosing a weak norm. And the weak norm's property is to be blind and be robust to high frequency noise. And this is explained in this experiment. I have the clean wave and I have the noisy one. The noisy one is what I'm going to use as a reference to do my inversion. And we do the same thing as the previous example, and I run the Wasserstein distance space inversion about 90 iteration and it stop. Once it stop, you see we still recover this Mamouzi benchmark you saw earlier. And on the right-hand side, this is the waveforms when it stop. The blue is the truth. The blue is the reference. It's a noisy reference we have. And the black one is the simulated data that the model produced. And this is when the model actually stopped. So look by our eyeballs, it looks like the blue and the black are very different. Indeed, they are very different by our eyeball norm, and they are also very different if you use the L2 norm to compare the difference. But the punchline is they are not that different in the Wasserstein metric. So the reason is Wasserstein metric not only measures the difference in vertical direction, it also measures things in horizontal direction. Because of the noise right now is very high frequency, although the vertical direction is very high, but I don't have to move much to cancel it out. That's why overall, the difference between the blue and the black is order 1 over n, where n is the frequency. So that's what you get. Yeah. So in a very different choice of metric, something that look apparently big can be actually very small. So this is really the power of choosing a different metric to be robust to high frequency noise. Okay, very quickly, I want to go to my third property, which is unique geometry. So far I've been focusing on how to choose the objective function J. And next I want to talk about the choice of M also play a role. M is the parameter. It's the parameter geometry that you want to do. So something we learned is that we learned a long time ago from functional analysis by Ritz representation. Derivative is not gradient. Derivative live in the dual space. So in order to pull the derivative to gradient, you need the inner product. That's where the Ritz representation come into the play. And the inner product is the geometry, is metric dependent. So by the famous work Jacob O in 1998, we know that if you choose a different dm, you get a different gradient. So equation 2 is the implicit Euler way to write gradient. And by natural gradient, I think that's what Olga, based on the abstract of your seminar's webpage, I think natural gradient is what Olga Mula talked about last year. So similarly, if you choose a geometry that is induced by the data manifold, you also get a different gradient. So combining 2 and 3, what I want to say is very quickly is that the gradient is really a choice. The gradient is not derivative. Derivative is decided by J. You don't get to choose. But gradient is something we can choose because we can choose which geometry that I want to update my M. So different choice of the geometry dm and dg can actually give you very different convergence result. So I just want to use one slide to explain this numerically. So I have the same Gaussian mixture optimization, same objective functions. That's why you see the same level sets. The level set depict the non-convex nature of this objective function. So J for both plots are the same. So what's different? Different is that I'm using different geometry to do the Ritz representation. I'm doing different geometry to pull derivative to gradient. One is based on the so-called L2 natural gradient. Another is the one based on the Wasserstein distance, the Wasserstein natural gradient. And more details, please see this paper on CISC. Okay, and the vector field, the blue like arrows, they describe a vector field, and this vector field is the gradient vector field for different geometry, and you already can see they are very different. And then if I start one point, the same point in the landscape, and my geometry or my gradient flow will follow this vector field. And because they have different gradient vector field, one diverge to a local minima, and the other one convert to the global minima. So I want to use this slide to highlight that sometimes we can steer our optimization to a global minima, not by changing the objective function, but by changing the geometry. Yeah, this is another power of the metric. And not in J, but in which metric space you are trying to find M. So this is about the space for M, or how you pull the derivative to the gradient. Okay, so finally I want to draw a conclusion, and then I know I need to talk about outlooks for the next 10 years. Okay, so my talk is focusing on a particular part of inverse problem. There's a lot one can talk about. What I want to highlight is even you cannot change the model, you cannot change the data. What we can change as users, there's still a lot you can play around. One is the choice of objective function or the loss function, how you measure the difference between the reference data versus your simulation. Another is in which space or in which metric space you want to find M. So why metrics matter? Because gradient is the direction the objective function increase as fast as possible. So that metric is exactly something to quantify as fast as possible, right? So different metric choice give you different fastness, and therefore you have a different gradient. So what I have shown you together with some intuitions is to, and some numerical results, and more details or theory, unfortunately, I don't have time to talk about here. You can find details of the theory in our papers. So something I have seen in the past decade of playing around those metric spaces is that you can gain robustness to noise. you can have a very nice optimization landscape compared to a very bad one. You can change the convergence speed, you can change the trajectory, and also change and reduce the computational cost. Whether optimal transport is a good fit for your problem or not is going to be problem dependent, and I hope by the end of this talk you have some insights on whether, whether your problem may benefit from such tools. Okay, a little bit output. This is really just my own 2 cents of what I envision the inverse problem community may have in the next decade. So I'm going to be centered around this optimization formulation of optimization problem of inverse problem, since this is where practitioners, engineers, they work with most of the time. I think I would like to computational inverse problem to be more geometric aware. So for example, choice of DG and the choice of DM to be more problem driven, and rather than like, okay, I like L2 norm here and I like Euclidean geometry here, so flat geometry. So that is the like standard choice, but those standard choices are not necessarily a good choice. And I think inverse problem will be more data realistic. For example, when we have multi-fidelity inverse problem, because your data come from multiple multi-objective, multi-fidelity, because your inverse problem come from multiple sources of data. And machine learning, well, nowadays, I think it's very hard to talk about the influence, not to now talk about the influence of AI and machine learning in our field. So I envision the next 10 years, this is going to play increasingly more and more pivotal role. And finally, we want the result to be certified. Currently, a lot of inverse problems are defaulted to L2 norm as objective function or least squares. And if it does not work, what do? We add a regularization. And the regularization sometimes are also there's a few very classical choices like TV, Tikhonov, and some variant of that. But regularization or explicit regularization can only play limited roles. Like there's some analysis on that even 30 years ago. It changes the singular value decomposition, but only a little bit. And okay, in certain, like say Bayesian inverse problem is another direction one try to solve. And in many cases, we just think the prior is some normal distribution, the likelihood is some normal distribution. Like Gaussian is the center world in Bayesian currently. So I think that should be changed to be more realistic. And finally, when we have the results, inversion result, I don't think there's like a systematic way for us to judge the benefit or the result. So either we already know the ground truth, we are in some so-called inverse crime situation, or we give the result to some expert, and then based on their 10-year or 20-year expertise in the field, they can see, oh, that look plausible. So if we don't know the ground truth, how do we judge the result? So something I feel could helpful is that we choose the metric. Well, this is centered to what I know very well. We can choose the objective function from the physics. We choose the metric also from the natural geometry of the unknown. We can use geometry as an implicit regularization. And for example, certain transport-based misfits can be helpful. And some of my current research endeavor is to design a metric that does not necessarily apply for probability distribution, but also apply for assigned signals. So I don't have to deal with the pre-processing that turn like waves into a probability distribution, because optimal transport is only encoded to compare probability distribution to by design. Okay. Another thing that I think we will need to focus on is many inverse problems, like probably the previous talk last week. Many inverse problem is not just inversion about one parameter, but it's the inversion over the physical law. Let's go through the examples. So the inversion from dynamics, what we have as example at the beginning of this talk. So in the data-driven dynamical system, this community, they really just want to understand the dynamics, but it's up to the user to parameterize the dynamics. So you can say, okay, my dynamics come from an ODE. Then you can be more concrete, saying, okay, learning the dynamics is to find the V in the right hand side, on the right hand side of the ODE. So that's one inverse problem. But you can say, okay, I want to go non-parametric. I want to understand the dynamics through understanding or getting a better grasp of the Kuhlmann operator. Okay, then that's another way of formulating the same problem, but now the focus is over the Kuhlmann operator. So I think when things like become beyond the parameters, we are talking about inverse problem over laws. So maybe there would be a unified way to connect different modeling assumption. So on one hand, I can have modeling assumption about recurring V, but on the other hand, I can have modeling assumption about the Kuhlmann operator, and they are clearly connected. I can either treat this as two different inverse problems, or I can find something that threads through them together, and that make it a system or a multi-stage inverse problem at different resolution that connect them all together. So that's something I think would be a very interesting research direction rather than focusing on a single one, but connecting many of them together for a joint goal, which is inferring inverse problem over the law or physical law. Okay, so another example that we can imagine could be learning a closure constitute laws hidden mechanism of a PDE. So that can also be considered as an inverse problem. Okay, so the last part that I want to focus on is to talk about things that would happen in the next 10 years is machine learning. So classical inverse problem is, okay, I have this data, I have this model, let's solve a PD constraint optimization. And then I spend a lot of time solving PD constraint optimization, dealing with noise sensitivity and poor optimization landscape. And finally, I end up with something I'm happy with, and my collaborator in geophysics is happy with. Okay, and then that's like several months work or even a year work in industry standard for one case study. But next time when I have new data, when I have a new model, I have to do this all over again. So there's a lot of wasted effort by repeating the same task again and again. So there's the knowledge stays the same, the tools stay the same. The only thing new in this repetition process is that I may have new data. So this is a very machine learning AI would be very helpful. And this is I see this trend more and more in both deterministic inverse problem and the Bayesian inverse problem. In Bayesian inverse problem, people also try to have amortized inversion. So you want to amortize the inversion over many experiments. For example, I want to learn the prior and the multi-scale representation such that if I have a new prior, I can have a new posterior sampling immediately rather than have to do the whole sampling process again. So I think this may be potentially be the dominating procedure 10 years from now when it's time to solving inverse problems. So machine learning can provide us fast surrogates for expensive PD constraint optimization. It can provide us fast surrogates for expensive posterior sampling. Mathematics can also enter. So there's the AI part, but mathematics is that if we solve the inverse problem in the machine learning architecture environment, there's new theoretical questions that we should address. So when you solve problem in the learning framework, you actually have a new inverse problem that is represented by measures. So there's new stability and approximation theory to address. And you also have uncertainty quantification, and the uncertainty quantification could be uncertainty over distributions, right? Rather than a single component, it may be distribution over distributions. And we also talk about out of a distribution or a domain shift and corresponding robustness or failure diagnosis. And also we want to have error indicator tied to the physics. So machine learning give us one result. Can we have a systematic way to flag, okay, that is not the result, good result. We need to pick the bad apple from the basket and maybe investigate the case a little bit more careful. So if there's any automatic error indicator we can design. So recently I wrote a survey paper in this direction together with collaborator Nick Nelson. So we have inject some of our outlooks also in this one. If you are interested, this is a good survey of what people have been doing in the past 5 years to do machine learning for inverse problem, but also potential open problems in the field. And finally, my conclusion is, I think metric design would it's very simple. It's just a little bit pause before you go on the computer. Pause a little bit to ask the question, what would be a good objective function? What would be a good geometry? Thinking through that sometimes can save us days or even months of work afterwards. And when a lot of algorithms right now are 2D and struggle with 3D and even struggle with higher dimensional or time-dependent data. We we really need scalable solvers, and the machine learning is one way for us to achieve scalability. Yeah. Something we need to do is also certify learning. Once we have the solution, we need to have a systematic way to say, is that a good solution or not? Especially in real situation when you do not know the true answer. Another thing that I want to highlight is the gap between our community and the machine learning community. In machine learning community, there's like a lot of image set, like MNIST or CFAR10, but there's none in our community. So we kind of do benchmarks by choice. So it would be nice if we have like open source data sets that everybody tests their algorithm upon. That I already see some results like OpenFWI in our community, but it would be nice to see more and more open data sets that everybody can test their methods on. And finally, there's like digital twin is quite big in the United States, and I'm sure it's also increasingly more and more prominent in everywhere in the scientific community. So inverse problem is a key component with digital twins, and how can we combine inverse problem alone as an essential part with digital twins to achieve very fast, short-time instant prediction and reference inference that also would be very important. So this is something myself also try to focus on right now. Okay. With this, I would like to thank you for your attention and happy to take questions.
Thank you so very much, Yunan. That was an excellent talk. Um, I've touched on this topic of optimal transport and inverse modeling many times, but nothing has ever been as compelling as your bar diagrams now moving mass. So thank you so very much. And also, I wanted to thank you for sharing really this in-depth outlook with lots of insightful comments for the next 5 to 10 years. This is really what we were hoping for when extending that type of invitation.
Yeah, thank you.
I just want to first, before I turn to questions, I wanted to make one comment relating to your second point here in the outlook. So we work a lot with modeling biology and neurobiology. And there it's the case that surprisingly many things are not known. Even maybe sometimes the physics or the basic biophysics, it's not known. And sometimes it's not really known if it's physics in a way either. There I'm thinking that, for instance, of remodeling in biological tissue taking place over many years, for instance. So in this setting, really learning laws or hidden mechanisms is really key. And it would be exciting to see where we can take that in the future.
Yeah,
And
I
maybe,
think
yeah, sorry.
oh, go ahead. Yeah.
So, and I thought maybe I could start with one question related to this. So in that sense, there's also often quite a bit of uncertainty associated with data, either uncertainty in the form of noise, as you touched upon here, or also other types of uncertainty that's more maybe regionally varying. Maybe I'm thinking of an example where you maybe have some kind of transport phenomenon, some convection diffusion, and maybe you're using some kind of molecule as a proxy for what you want to measure. And it's unclear, for instance, if that molecule reaches your whole domain, for instance. I was wondering if you could say a little bit about any thoughts on robustness of these methods to uncertainties and variation in uncertainty.
Oh, yeah. So, yeah, noise is everywhere, especially in this dynamical system problem. Yeah, like modeling. So maybe I jump to that picture. That's another thing I didn't talk about, but I have been working on in the past 5 years with two graduate students. Really, they're this is a full blown on this. So problem like that is exactly people use in biology and some other physics to model what's going on. It's tons of noise. What you observe is noise, and the model is quite unstable, like say chaos going on. So something that I've been trying to work on is to not work on the point-wise, but to do distribution matching. So let's say you observe data, but I don't really trust a lot of what I observe. So either what you observe is already noisy, or if you don't trust what you observe, you inject some noise yourself, for example, by convolution. Then you can, one way or another, turn your observation to distributions. And then I'm trying to solve the inverse problem over the space of probability distributions. So I want to turn, if my data is elevated to a distribution, I find a way to turn my model into something that turning one distribution to another distribution. And then right now, your model is not just mapping one-to-one, you are mapping a distribution to distribution. And this whole modeling assumption already give you tons of robustness. Because when we match two distributions, we are not matching particles like pointwise. We are matching, okay, the law of this is similar to law of that. So the ambiguity of a law or the ambiguity of a distribution itself is a nice buffer for us to be robust. Of course, robustness always come at the price of accuracy. This is always true in linear algebra as well. Like if you have a nice model that's low rank, inversion of that model is terrible. You have a terrible condition number. So one cannot achieve both accuracy and robustness at the same time. But if robustness is the concern, then going for weaker modeling can really help. So we developed actually since I connecting Matt Colebrook talk probably not last week, we have a Kuhlmann operator on the distribution level, and we call it distributional Kuhlmann. So that Kuhlmann operator is dealing with aggregation data, the distributional data, and that Kuhlmann operator inherit all the property of the determinist Kuhlmann operator, but can also evolve variance operator. So you can see how variance propagate or how expectation propagate. So all those things can help. Another thing I've been working on is like Takens embedding. It's very powerful tool in dynamical system. Yeah, oh, you know about, okay, great. So one of our recent work is to leave the Takens embedding from a point-to-point result to a distributional result. Yeah. So if I can think about Takens embedding on distributions, then I can do delay embedding on distributions. I can do the entire learning and the modeling on distributions. Then I can gain a lot of robustness. Yeah. Yeah, I can send you some paper relevant to that afterwards if you're interested.
Super, thank you. I also know that Thomas has a few questions, so
Yes, I do.
avoiding taking all time, I'll send a word to you, Thomas.
Thanks. Yeah, and thanks again for the lovely presentation. I've seen optimal transport described many different ways, but I feel like the graphical representation that you had was quite understandable. I was curious about a few things. So one of them was on page 21. You described a situation where if you use the L2 norm versus some kind of Wasserstein norm, that you had this very favorable situation. Is this generic, or is this just this particular situation that that would give you this property here?
I think yeah, this is a very good question. I wouldn't be able to claim. That's why this part of it still stay at the inside or numerical observation. I wasn't able to have any theoretical guarantee to declare this is something generic. But we do know is so the gradient direction is so that it comes from the local approximation. So when we do the approximation of let's say Taylor expansion of in L2 geometry, we get a perfect round ball. But in Wasserstein geometry, there is an operator L inverse with the inverse elliptic operator. So this is the integral operator kind of show up earlier. So this is a weighted elliptic operator. And when you have that, rather than a ball, it actually become a bigger ellipse because of the smoothing effect of the inverse elliptic operator. Also, in the paper, you can actually see the ball figures and the ellipse figures. So I think that cause that is a reason why it has a different direction. but whether the direction can always drag you out of local minima, I think what I can say for this example is that because I have a different dynamics or different vector field, then the Bayesian attraction for this global minimum on the right-hand side is bigger than the Bayesian of attraction for the left-hand one. I think that's something I can claim.
Mhm.
Like which we also see. The Bayesian of attraction, like everything I start from this region, I would be able to converge.
Mm.
But in order for the left-hand side, if I want to converge the global minimum, I have a smaller Bayesian of attraction. One thing that I want to do is to have a simple case where I can analyze the Bayesian of attraction or characterize the Bayesian of attraction. Then that will give this a theoretical guarantee.
Mm.
But hand wavy wise, I think what people observe all the time is when you have a weaker geometry, the smoothing really smooths out some of the rough landscape. So when you are in the weaker norm, you can expect a better landscape. Yeah.
So thanks, but I'm still curious about this because at least if I think about, let's say, classical statistical learning, right? Where I say, I have a model M. Let's not call it M because you called it. Let's say I have a model F, and F takes in two parameters. Let's say M and because I have to change what I wrote down, M and I guess theta, right?
Yeah.
And then outputs Y. Right, and I have pairs of observations between M and Y, and somehow I still want to be able to match this model M or F, sorry, in your case, F of M comma theta. I want to match that to Y. And then in many cases, at least I can get somehow an estimate on what the noise looks like in these observations. And oftentimes people will say, oh, well, this noise is at least in every pixel in my image appears to be Gaussian, or as a whole over the whole domain appears to be Gaussian. And because of that, I can formulate this as a maximum likelihood problem, and then I get a least squares problem out of it. If I have some other kind of observation about the noise, then I can get some other kind of loss function that's also implied by the noise in the observations. And so that sort of naturally leads to least squares problems, that naturally leads to logistic regression and so on. But is there a connection here? Because I don't see this sort of natural connection to the
Oh,
Wasserstein,
I
because the
see.
noise, why would the noise be somehow in this kind of loss landscape?
Oh, okay. So that motivation, that intuition that you just mentioned, the mechanism come from Bayesian, because if you assume the noise, if you assume the noise is Gaussian, then you automatically have a likelihood, and the
Mm,
likelihood would, well, the likelihood is not this, but the negative log likelihood is the least square.
right.
Yeah. So that's fine in Bayesian, but once you take a negative log likelihood, you make it from a Bayesian posterior to something that you want to find the maximum posterior MAP point,
Mm,
maximum posterior point. That become a deterministic inverse problem.
right.
So I think the connection here is broken once you turn to a deterministic problem, because once you turn to a deterministic problem, you have a multimodal landscape. So
Yeah.
in posterior, maybe you have a multimodal distribution, but now you have a non-convex optimization to solve. And that choice, well, if you have global optimization, it's fine. But if you have gradient-based optimization, it's not really okay. So that's why if I don't think about Bayesian, just think about it as a purely deterministic optimization, I would benefit from choosing a different loss. And actually, I have a work with Matt Dunlop. I think it's called the stability of Gibbs measure Wasserstein. Yeah, I can send you too.
Yeah,
So we
please send it
actually
to me. Yeah.
characterize the Wasserstein distance as the likelihood, as the
Uh-huh.
potential, and you can actually define the corresponding noise assumption behind by choosing Wasserstein distance as the loss function.
Okay, yeah, because that's still the thing that gets me is like there's going to be some noise in the observations that are going to inform how I would choose this loss function
Yeah,
ideally, at least from a
yeah.
classical sort of inverse problems perspective.
Yeah,
Yeah.
statistical learning, I agree. That's how the Bayesian framework starts. But I think it's a modeling assumption. I can either solve an inverse problem by deterministic world, or I can solve an inverse problem by statistical learning or Bayesian world. And a lot of what I focus on in the talk is the practical aspect of it, like the
Mm,
computational part of solving it.
mm,
if I want to solve a nice problem, this objective function will help me more than the other. Although this choice may have a less statistical meaning behind it. Maybe
I
that's
see.
more toward your question. Yeah.
Yeah, yeah, it goes in that direction. I mean, I guess you could say that getting a distributional estimator as opposed to a point estimator
Yes,
is just
precisely. You are
inherently
different
risk
world.
averse. Yeah.
Yeah,
It's
you are in
inherently risk
different
averse,
world.
right? Yeah.
Yeah.
And then I guess before we run out of time, the last question I have is you mentioned in the Outlook section at the end um, something about the like learning operators and
Yeah.
things like that. I think it was
Yeah.
in this, but yeah. So I don't know this question, but so are there any kind of error bounds for these operators, A theta,
Hmm.
when you actually take into account how you obtain those operators numerically?
Oh, so people, yeah, okay, that's a very good question. I think most of the analysis, there's a lot of analysis, like for example, by Martin de Hoop, Matty Lassas, there's a lot of very theoretical work around learning inverse operator. So most of the work assume there's no numerical artifact, or
Mm,
assume or the numerical aspect of learning is going to be epsilon level. So a lot of work is more about the universal approximation theory. Or
hmm
so in terms of for example, you are operated this space, but you are using a subspace of that, so you have approximation gap, or you have an insufficient amount of data, so there's like a sampling gap, but not so much about the numerical gap.
mm,
So I guess numerical aspect in this world because it's manifested in terms of training. So maybe you don't train to 100% accurate, you train like say 10% accurate. And how the 10% is in the training error. And then how the 10% training error is translated into generalization error. That could be, I can see a generalization error analysis.
Yeah, I think that would be quite interesting. I mean, especially from the perspective that if the training is done using some kind of stochastic approximation method like stochastic gradient descent or atom or something like
Mm-hmm.
that, this
Mm-hmm.
the resulting operator that I get has very few guarantees, right? So then from
Mm-hmm.
the, and then if you want to use this inverse operator in a critical setting, then you have to be quite careful about that, right?
I see that. I
Yeah.
think there's it's a very interesting direction. I think it's not very well addressed in the community based on what I understand from writing the survey paper. It
Mm,
is maybe one can have a simpler setting, let's say approximating a linear operator, and then like for a linear inverse problem, and then ask the same question. So this is about stability respect to numerical training error. Yeah,
right.
that would be very cool. Mm.
Yeah. Thank you so much, Yunan. So, are there any other questions? I know I took up a lot of time. Uh,
If you have a few more, if you have 2 more minutes, Yunan, we have a
Yeah, I
question
do.
in the Q&A from Baltasar Lorenzo, who comments that this was a very nice talk and has a question about computation.
Okay.
So Baltasar
Uh,
says, computing the
yeah.
exact Wasserstein distance is usually expensive and scales poorly with dimension. But what computational strategies are you using to make the Wasserstein-gradient dynamics computationally tractable for the dimensions you have, for instance, in the context of kinetic PDEs? So,
I totally understand. That's one of the concerns. So, as you see, computing Wasserstein distance by itself, it takes an infinite problem. So I didn't talk about that myself, but there's a lot of people working on the frontier of pushing the computational cost of Washington distance computation to lower and lower side. So if we are in, for example, what Bata is talking about, like 6 dimension, that is very hard to do by grid-based method. So something people have been doing is some alternative like slice Washington distance. It still have the Wasserstein distance nature, but it's like projecting one dimension and do one-dimensional Wasserstein distance and then integrate over the 6 dimension or spheres. So that's what people have been doing. Another is a variational approach. So so I think he mentioned or she mentioned Wasserstein gradient flow. So Wasserstein-gradient flow, if you have like a 6 dimension, one of the way people have been doing that I see in the community is to use machine learning to give you the update. So rather than solving a 6-dimensional PDE, you have a variational form because JKO have a variational form. So as long as it has an optimization, maybe I can use machine learning to help me through this high-dimensional difficult part. A third pathway is to do particles, but particle method, I would say 6 dimension, it still have its limitations. Like we say particle method does not have a curse of dimensionality, but it does. Because if you want to have accuracy, it's number of particles per cell that really matters. So when 6 dimension, you still need probably a zillions of particles. So yeah, I think most practical approach would be alternative like slice Wasserstein distance or have a neural network surrogate in your Wasserstein gradient step. Yeah. Okay. I
Thank
hope
you. These
he's
are
not
very
here anymore, but I hope it's
excellent
good.
pointers.
I'll
Yes.
see him tomorrow.
Thank you.
Okay.
All right. Great. Then I think that's it. We've definitely gone over an hour, so longer than we normally do. Thank you so much, Yunan. This was very, very interesting. And if you can, also please send Marie and me the references you mentioned, and hopefully we can continue talking in the future.
Yeah, certainly. Yeah. Thank you very much for having me. It's my pleasure. Hope to see both
Yes.
of you in person sometime.
Yes, likewise.
Yeah. See you.
Bye-bye.
Have a good day.
You too. Bye-bye.